Beneath the stepped silhouettes of Sumer's Ziggurats lies a forgotten marvel, a water network that turned desert mud into thriving metropolises. Engineers over 4,000 years ago moved millions of liters through clay arteries, feeding fields and fountains alike. How did a civilization without steel or concrete achieve such precision? Around 3500 BCE, the fertile floodplain of the Tigris-Euphrates gave rise to the first true cities, Uruk, Lagash, and Uar. Each spring the rivers burst their banks, moving as much as 1.2 million cubic meters of water along a 30-kilometer corridor. To harness this force, the Sumerians cut a network of primary canals. The most famous, the Irrigation, was 12 meters wide and 3 meters deep, carrying water directly into the heart of each settlement. From these arteries branched secondary ditches, some only 0.8 meters deep, which spread into residential blocks and could deliver water to any house within a 500-meter radius. By 2500 BCE, the city of Ur alone boasted a canal system extending 150 kilometers, irrigating fields that produced an estimated 3 million kilograms of barley each year and supporting a population of roughly 65,000. Earthen levees up to 4 meters high, such as the massive wall protecting the temple precinct of Nana, restrained seasonal floods, and shielded granaries storing up to 200,000 cubic meters of grain. This hydraulic backbone created a reliable surplus. The excess fed the labor force that raised the stepped Ziggurats, including the 21-meter-high Ziggurat of Ur built around 2100 BCE, whose 3 terraces once glittered with glazed bricks. The waterworks of Sumer thus turned a volatile river valley into a cradle of urban civilization. The Great Ziggurat of Ur, erected circa 2100 BCE, rose 30 meters on a 64 by 46 meter platform. Beneath its terraces lay a concealed reservoir capable of holding 200,000 liters of water, enough to sustain the temple staff for 3 days without external supply. A 3-meter-wide stone-lined channel entered the base, linking directly to the city's main canal. From there, water cascaded down a series of stepped basins, each lined with bitumen to prevent seepage. These basins acted as settling tanks, removing silt before the water reached the upper levels. At the summit, a bronze-capped basin collected rainwater, feeding a small hydraulic lift that raised water to the shrine of Nana, the moon god. This dual system, river feed plus rain capture, ensured a constant flow, even during drought years. Sumerian engineers fashioned thousands of baked clay pipes, each 15 centimeters in diameter and up to 2 meters long. The pipes were sealed with a slip of fine clay, creating watertight joints that survived centuries. Excavations at Nippur revealed a network of 1,200 meters of pipe running beneath the temple courtyard, delivering water to ritual basins and public fountains. Flow rates were calculated at 0.03 cubic meters per second, enough to fill a 10-meter-wide pool in under an hour. Some pipes incorporated a slight gradient, about 0.5%, to maintain gravity-driven flow without pumps. The most sophisticated segment, discovered at Eridu, featured a pressure-regulating chamber that balanced water levels between the lower and upper terraces, preventing overflow during the spring melt. This mastery of ceramic hydraulics predates Roman lead piping by a millennium. Sumer's flat, alluvial plain made the great cities of the 3rd millennium BC perpetually vulnerable to the Euphrates' sudden surges. To shield the towering Ziggurats, engineers erected a series of earthen embankments called Ziggurats, each averaging 3.5 meters in height, 12 meters in width, and extending up to 250 meters along the temple precincts of Ur, Nippur, and Eridu. At the Great Ziggurat of Ur, a secondary embankment was shaped into a U-shaped basin measuring roughly 180 by 90 meters. Its capacity of about 150,000 cubic meters could hold the runoff from a 3-day storm. Overflow channels were cut with a precise 1-degree gradient, guiding excess water southward into the marshes of the Shat al-Arab, where it rejoined the Euphrates downstream without eroding the sacred core. In the flood of 2240 BCE, river levels rose 2.8 meters, enough to submerge low-lying fields. But the Ziggurat held firm, keeping the temple's reservoir intact and protecting 12 tons of stored barley and the bronze statue of the goddess Inanna. This resilience was no accident. Cuneiform tablets from the archive of Enmerkar, dated to 2255 BCE, record water height measurements to the nearest centimeter, flow speed calculations of 1.2 ms superscript 1, and a 10-year schedule for reinforcing the embankments with woven reed mats and lime-based plaster. The meticulous data-driven approach of these ancient engineers turned flood-prone terrain into a cradle of civilization. The principles honed on Sumerian Ziggurats echo in today's irrigation. The concept of tiered reservoirs mirrors modern multi-stage dams, while the use of gravity-fed clay conduits anticipates contemporary PVC networks. In the 19th century, British engineer Sir William Smith cited the Sumerian water tower as inspiration for the first pressurized water supply systems in London. Even today, Iraqi farmers restore ancient canal alignments, following the same 12-meter-wide channels that once fed UR. Satellite imagery shows that over 70% of current irrigation routes in southern Mesopotamia overlay Sumerian foundations. The ancient engineers proved that sustainable water management could thrive without modern machinery, a lesson that resonates as climate change strains today's water resources. The hidden hydraulics of Sumer's Ziggurats show how ingenuity can tame even the harshest landscapes. Next time we'll travel to the deserts of Egypt to uncover the lost solar technology of the ancient sun temples. Subscribe now and never miss a secret from the past.